say in Polish, to jest instytut, gdzie pracuje się na obrzeżach fizyki, bo perimeter to jest obrzeże. Ale usłyszałem od Kosteckiego, że jest tendencja jednak, żeby
do środka
zajął się fizyką. Okay, so we'll learn about the foundations of quantum mechanics and some military aspects that you see
yes.
in the subject.
Yeah, I decided to add it. Actually, I don't remember my original motivation for using this word. Maybe it was some information about the state of the Eastern Front, or maybe something else. I don't remember precisely. But anyways, so I would like to start from a long citation, which I found very inspirative a long time ago, and I think that basically this is something that summarizes the direction of all the stuff that I will be telling you later on about. So actually I will read it. Okay, so I will do it. Unlike the Riemannian manifolds, the quantum mechanical unit spheres do not differ one from another. They are all isomorphic. The words of the present-day quantum mechanics thus present a picture of structural monotony. They are all painted on the same standard, isolate, symmetric surface. The formalism of the quantum theory of infinite systems and quantum field theory is not very different from that. In spite of several mathematical refinements, the introduction of sister algebras, the Galton-Segal construction, the basic structural framework of the theory is conserved at the cost of quantitative multiplication. When meeting a new level of physical reality, the quantum theory responds by simply producing infinite tensor products of its basic structure. And maybe that present-day quantum theory still represents a relatively primitive stage of development and lacks some essential evolutionary steps leading towards structural flexibility. If this were so, further development would involve a program opposite to the quantization of gravity. Instead of modifying general relativity to fit quantum mechanics, one should rather modify quantum mechanics to fit general relativity. After all, most of the essential progress in physics has been achieved by denying something apparently obvious. So, when I started
to była część artyleryjska.
Przygotowanie, tak?
So when I started, so the personal part in it for me is that when I started my PhD in quantum gravity, and somehow I met this work, this paper with this text precisely at the moment that I was very, very doubtful about the quantum gravity in general and also quantization in particular. And so this what I'm going to tell you about is precisely about the idea how to go beyond quantum mechanics, how one may try to go beyond quantum mechanics using some geometrical structures that pop out there, and the long-term goal, which I will not speak here about, but the long-term goal is maybe that like maybe the rapprochement between general relativity and quantum theory should be done from side of enlarging the structure of quantum theory beyond quantum mechanics and not quantizing gravity. But this is beyond this stuff. Okay, so just to put everyone on the same ground, this is like how the very brief story of standard formulas of quantum mechanics looks like. There is kinematics is defined by structures on Hilbert space, so we have density operators and Safadjian operators. The dynamics is of quantum states is defined by two different mappings. One is associated to so-called closed system evolution, and this is provided by unitary operators, and there are projective measurements. And this is what I call semantics. I prefer to use the term semantics, like physicists usually would say theory of measurement or interpretation, but I think that it's a better term to like cover both of them in one short phrase. The semantics is that we don't deal with the data that we measure directly using the formalism of Hilbert spaces and operators, but first we translate those mathematical structures into probabilistic setup using spectral theory and so on, and only later on we compare data with results of probabilistic statistical inference.
Tu się panu przewróciła literka do góry nogami.
A tak. Jakoś te sigma algebry przyzwyczajem się pisać przez mcho, a nie przez omegę, bo omega to jakoś tak ze stanem podstawowym GNS-u mi się cały czas kojarzy. So the questions that one may ask to this standard setup is it possible are like the following. I will go along more structural line. All those things could be approached more conceptually and expressionally, but I prefer like to go for mathematics because it's more like less discussion is required to find common ground. So one question is it possible to eliminate Hilbert spaces from the mathematical foundations of quantum theory? And one of the approaches that was proposed in past to solve this problem was this algebraic approach. Another question is it possible to provide geometric, not algebraic, but geometric foundations of quantum theory that would allow for nonlinear generalization of quantum kinematics and dynamics? And I would like to show some, I think, good evidence that it's possible using quantum information geometry that we'll tell you about. So, like the main goal of this, what I will be telling about, is to propose a construction of foundation approach to quantum theory, which would be based, which would utilize the virtues of both algebraic approach and geometric structures that appear in quantum theory, in the mathematical structure of quantum theory, to propose something that goes beyond quantum mechanics. So both in kinematics, in dynamics, and also interpretation or in semantics. So main insights that would serve for this purpose, and from which I will start. One thing is that both probability theory and Hilbert space setting for kinematics of quantum theory. So quantum states as density matrices and over Hilbert spaces and observables as adjacent operators on Hilbert spaces. They are actually can be considered as two special cases of integration theory of double-star algebras. I will say what they are in a moment. Right now I just want to paint the canvas and then I will give some definitions. So in this setup, quantum states can be strictly understood as positive integrals, and quantum quantities, so observables, can be understood as self-adjoint integrals, so something that those states act on as integrals, something that is integrated. So if one thinks of what the spaces of quantum states would be when one doesn't have anymore any sort of Hilbert space in the background, then one would consider just subsets of those positive integrals, and mathematically they are defined as positive parts of Banach duals and double-star algebras. I will also say in a moment what those objects are. And this would be like this would be used as a starting point for this construction. And the thing is that like this missing structural flexibility that was pointed out by Mielnik, the idea is to add this flexibility by considering different geometric structures over those spaces of quantum states. And the main structure that would play the role of this, the main geometric structure that would be used would be, there would be various quantum relative entropy functionals. And they will be used to define different geometries. And those different choices of relative entropy functionals of states. Relative functional, I will also tell the details in a moment, but you can think basically that relative entropy is something like non-symmetric measure of distance between two quantum states. Basically it produces, it takes two states and produces you a number between 0 and infinity, including including both edges of this. So it can be 0, it can be infinity. And this, if you add additional properties to such functional, then you can get more interesting geometries in principle. And so, if you want to do various things like estimation of quantum states, like trying to say how one state is far from other state, then such quantification of distance provided by relative entropy is in principle, well, sufficient. I mean, it's super abstract so far, but you can think of it that it's reasonable to use such object to do estimation and inference. But the idea is that if you look at it, whatever, in this totally abstract picture, you can think of it that you have already like spaces of quantum states that are equipped with some geometric structure, and well, maybe those objects, those spaces equipped with this geometry, might be interesting object of study, and one can try to run further construction of quantum theory beyond quantum mechanics from these structures. Okay.
History of physics teaches us that it has never happened so that one would introduce new mathematical concepts before there were any experimental indications that they are necessary. What about the experiments? Where
Well, I would say that
is this connected with experiments, and where are indications that this is really a useful concept? Those experiments are not described within the present framework.
So I would say that, like, if one looks into literature of quantum measurement and estimation and so on, those various relative entropy functionals are used on a daily basis.
But where are the experiments that require
the
this?
need for generalization.
Experiments for, I would say that there is
That
not.
indicate that the present framework is not adequate.
Okay, so I would say that there is a difference between model within framework and framework itself. Frameworks are never, well, it's actually a good question for philosophy of science, so we go to meta theory.
No, it's a very practical question.
No, because there is a difference between framework and a model within framework. It's a model that is falsified or verified, while frameworks are just tools for the construction of models. So this what I'm saying here is about framework for model construction, which might be found relevant or irrelevant by people who construct specific models for analyzing specific data sets. So like and that's why also my motivation and my goals are structural. I'm not solving the particular experimental problem. My aim is to provide a framework which might be structurally and aesthetically seductive with respect to current theoretical problems, but not with respect to experimental evidence. I think it will be more clear later on.
But do you know how to solve, for example, I don't know, spectrum of the hydrogen atom in this framework? Or it is only the concept without any possibility of prediction of experimental results?
I think that it would be nice if you could ask this question at the end, because so far we don't know what I'm talking about.
Yeah, so
It could continue this way.
Okay, so the starting point. Well, I mean, in the last recourse, I'm not using this recourse yet, but in the last recourse, I always can defend this as nice mathematics that I want to present to you. But I'm not doing this argument yet. So let's continue, and you will see whether you will find it useful for yourself, actually. What I want to start you from like quick revisiting of the interesting structures, like basic structures in probability and quantum theory, to show that there are like very interesting similarities, and one can see that basically. Actually, I wrote it too complicated, but basically, like probability densities are elements of positive cone of L1 space, and there is a strict analog of this. These are positive cone of trace class operators. Okay, so these are bounded operators on Hilbert space, and I think everything else is pretty standard. Yeah. So when one tries to do like some sort of any sort of statistical inference, or most of types of statistical inference, one starts from postulating some sample space and considering also some probabilistic model. You assume that something is Gaussian, or so on. And then the problem is the typical problem is to estimate, for example, mean and variance of Gaussians, which means actually searching through the space of all Gaussians for the particular point in the space. So the space of Gaussians is a specific probabilistic model. In various problems of quantum estimation, there are similar situations that you have some space of quantum states that you, by some reason, want to find the most probable state that was that fits to the data that you have in hand. And so, like, consideration of some specific subsets of all positive trace class operators, of all positive density matrices, is fine. Here I don't assume normalization because normalization is basically all mathematics works without normalization. Normalization is really necessary for frequentist interpretation, but you can do at least some sorts of statistical inference without assuming frequentist interpretation. So, so once you can see that there is a lot of similarity. To those of you who are not familiar with the Banach space duality, it's basically if we have a Banach space, then the space that is dual to it is a space of all linear functionals that are continuous, and this space is becomes equipped with the supremum norm, and then it is again a Banach space. So the thing is that if we apply such construction to our space, we get L-infinity space, and if we apply this to trace class operators, we get bounded operators. So somehow you can think that the space that is a container for quantum states, when you do Banach dual, you get the space that is container for all observables, which is interesting thing. And the natural question is like, okay, here we have some setup for quantum states, here we have some setup for probability, for doing probability theory. Can we do can we do both at the same time, or and also something more general? And the thing is that yes, we can do it using the abstract notion of so-called W-star algebra. It is defined here. Basically, you can think of it that this is an algebra that is at the same time Banach space. It has an abstract version of the adjoint operation that we do on operators.
By the way, the previous Banach spaces were understood as real, not.
Okay, so here is real, but you can do complexification of those.
Yeah, but
also
you don't need, because
yes.
in physics, and the same is here, that you may limit yourself to real
ones. Yes, yes, but it's somehow we are more used to do real integration in case of probability theory and
yeah, but still you may, because both density matrices and observables form a real Banach space, yeah?
They belong to real. Yeah, yes, yeah. Self-adjoint to self-adjoint, not just real Banach space. Yes, yes. So basically, we might think of, okay, so we just take some algebra with additional multiplication, with its Banach space, we add something which is just an abstract version of an adjoint operation. Then we require that all those operations, all those algebraic operations are continuous with respect to the norm topology. And those 4 points, they define so-called sister algebra. And then we require that there exists a so-called predual Banach space, which means that basically there exists some additional Banach space, such that when we dualize it, we get our Banach space.
So it is a different star, right?
Well, one is on the bottom, other was on the top.
Yeah.
So far, it's just a symbol. You can think of that.
No, but this star in the.
Oh yes, because
the top is different than the star.
Yes, because it's here. There's like 6 small things going out of the center, and here are 5. So they are different.
American versus Jewish.
Actually, I think it's, I always thought that it's like a Soviet star, but
So this W star refers to which star?
W star refers to this star, because basically it comes from C star.
Which is like dagger.
Yes. Okay. So why do we require such extra condition? When you look here, you can say that, oh, I start from L infinity, and there is actually a space which is pre-dual, and this is L1. And here I also can start from B of H, and there is a pre-dual. So the idea is that let's start from the space that contains observables, and this is like W star algebra, and or actually C star algebra, and let's require that we have enough states, enough interesting states. Okay, and this is just, well, just put it into the definition, and that's all. And now, like, the nice thing is that, like, there are very specific algebraic conditions under which this setup reproduces the things that were on the previous slides. So if this algebra is commutative, then there exists a measure space such that we recover this probabilistic setting, and if we require some purely algebraic condition called type 1 factor, then there exists a Hilbert space, and we recover this setup for doing density matrices and operators in Hilbert spaces. This is like this conditions basically specific properties of projections within this algebra. There is even nothing topological in this condition. It's just relevant for whatever I will be telling later on. So the nice thing is that the conclusion from this stuff is that we can consider, at least we can consider the possibility of consideration of those positive parts of reduals of arbitrary W star algebras as a nice candidates for quantum states, for like general notion of quantum states. That in specific case we get density operators, in specific case we get the probability densities. Okay, so like tentatively, I would call arbitrary subsets of those positive parts of reduals as general quantum information models, which is just continuing the same story that I had here, arbitrary subspaces of positive parts of reduals. And actually, if n is commutative, that we recover those probabilistic models. If n is a type 1 factor, then we recover those spaces of density matrices. Okay, this is cool. But the thing is that why actually this definition really is useful and makes sense. The thing is that like the setting of W star algebras is not only allowing to recover just known things, like on the level of algebra and on the level of states in specific cases, but actually one can generalize full theory of integration to from commutative setting to the setting of W star algebras. It's a super non-trivial thing. It's actually why it should be possible. So there are like non-commutative versions of partial integration and so on. So there are like there are non-commutative LP spaces and a lot of interesting results. Virtually everything what is interesting can be generalized there. And this means that actually we can work with those W star algebras as a generalized setting for integration theory. Okay, but now one can look back on the ordinary setting of quantum mechanics and see that we had this quantum mechanics and there was a probability theory, and we used probability theory, which is just a special case of this general setup for non-commutative integration, to get to data. So the idea is that maybe we can forget about probability theory and all the foundations of this quantum theory beyond quantum mechanics, and directly use this integration, non-commutative integration theory to build up generalization of all statistical inference tools, and just construct quantum models and do all those things that we want to do with data, do all inference about data directly using quantum models without passing through probability theory.
What is a physical example of these epistemic data that seem to be important? do they differ from data?
You can ignore the word that is there.
Okay. Thank you.
What does it mean? The word.
You can ignore it.
This is again something that I mean this makes sense. I mean, if I would be able to start philosophical discussion, that I would defend this, but I low level at this like no philosophy mode, we can just ignore this phrase, and I think it would be better. Okay, so this is once again like this what I just told before by waving my hands. So here we have some data, which are right now called experimental, probably to distinguish between like data in my brain or whatsoever in my head, or I don't know. People just use this term experimental data. Actually, I don't need to defend it. So and do some methods of statistical inference with like associating constructing some probabilities and so on, and they transfer it. And on the other hand, we have like various methods of constructing like particular operators, for example, like quantization and so on and so on. So, okay, so here is like one theory, statistical inference theory, which is independent. Here is another theory, like quantum mechanics with its additional tools. And this what is like verified against data and experiment is really just all this setup. Okay. So if one observes that in principle like this quantum states can be considered as generalization of this, and the framework for quantum states can be considered as generalization of probability theory, then the idea is just to start from for quantum states immediately and construct statistical estimation tools here and just associate them with data. And then the kinematics, the idea of construction of kinematics would be to build it as similarly to one constructs structures on probabilistic models, and the dynamics could be interpreted as inference, actually causal inference. I don't know to what extent the notion of causality coming from inference theory is known to you. I will return to it later. So right now, okay, and the idea is then, but when we just start from double-star algebras and states, and we don't wish to go for superspaces and don't wish to go for probabilities, then we cannot use spectral theory. Yeah? Like spectral theory is like, and all this thing that I call spectral paradigm is precisely about calculating values and then associating those things with doing probabilistic estimation. Yeah? Because we put those eigenvalues here as points of the sample space. So there has to be another tool that would allow us to select particular states and define their dynamics based on data. And this is the point of introducing those information geometric structures. Okay, so within this...
So this will replace this probability theory, right?
Yes, using probability theory and spectral theory.
If you want to have the statistics, you must have something.
Something, yes. And the thing is that to do directly statistics on quantum states and associating this directly with description of data. So okay, so to go more and more into mathematics right now. The starting, one can think of all this story that I told so far as a postulate to consider expectation values as more fundamental than eigenvalues, and as a result consider spaces of expectation functionals as more relevant than spaces of eigenvectors. And like if one starts from this, then subsequent changes have to be applied. So
and what would be the dynamical variables here? Momentum, angular momentum, such.
you mean what would be observables?
Yes.
Observables would be arbitrary real-valued functions on those spaces of quantum states. this in particular includes, and I will tell about this, it includes all self-enjoying operators as special case. I will tell a little bit about this in a moment. So like one thing is like movement generally moving from eigenvalues to expectation values, which means moving from spaces of eigenvectors, so Hilbert spaces, to spaces of expectation functionals. So these are like those models, quantum models. And next, instead of defining observables as operators on Hilbert spaces that have real spectrum, observables would be defined as real valued functions on quantum models. And then the geometric structure provided by scalar product would be replaced by geometry that would be defined by quantum relative entropies and quantum structure. And maybe just even now I will give you some hint why this is a bit reasonable. Like when one writes this sort of geometrization of finite dimensional quantum mechanics, like doing projective, like working on projective Hilbert spaces, then maybe I should use some symbol that is reasonable. Minus, plus, I don't remember, but there is something like this. So this is like scalar product on vectors, and one can rewrite it in terms of geometric terms. This was like things that were done mostly in 80s and rediscovered by some people many times, and actually going back to even to
this is a
70s.
Kähler structure.
Yes.
So this was discovered in 20s, I believe.
Maybe, but not in context of quantum mechanics, I think.
No.
So the thing is that like one can rewrite the scalar product and forget about scalar product and just work with Riemannian metric and with which is scalar and with symplectic form. And then one can define, for example, one can say that instead of speaking of unitary of dynamics defined by unitary evolutions, one says that dynamics is defined by Hamiltonian killing vector fields and so on. So there's this like.
Is there a superposition principle still retained, or?
I'm actually not a believer of superposition, so I never.
I'm not asking of your beliefs. I'm asking whether it is retained.
Yeah, but there was like comma in my sentence. So the second
Yes.
part of after comma was that. So I was never asking this question to myself, so I don't remember, but I may think of it. Like the setup is constructed bijectively, so I suppose that yes, because it's like there is like one-to-one between all those structures in this standard setup and this one, because it's basically consideration of CPN. Just like just one takes. I never know how to write it. Like CPN minus one actually. And this is like all those structures work on this. So, so here I think that if one wants to have a superposition, then one has it. Okay, so basically, like here, those structures, one can think of them as generalization. So instead of dealing with Riemannian metric, one will deal with relative entropy functional. And instead of dealing with symplectic form, one will have Poisson structure that in general will not be symplectic. Why this is a generalization, I will show you later on, but basically under some conditions which leave space for many different relative entropies, second order Taylor term of relative entropy is very often, under some conditions always a Riemannian metric. So those two structures are actually in a strict sense generalization of working with those structures. This is for those of you who kind of are familiar with this with this perspective. The thing is that this guy works only for CPN, so, and this you need to have finite dimensional structure. While here, everything is, I mean, it's functional analysis from the beginning, and you don't need any dimension. So, I mean, finite dimension. Okay, so, okay, so I told you already about this, and the thing is that the next idea is that, okay, we have.
So once again, so what will be on the left hand side in your setting is some.
Oh, there will be.
There will be this distance, yes, or somehow. Not the distance, but some.
There will be nothing on the left hand side. The point is to deal with those structures independently, and in some specific cases, some special cases.
Like there may be some. Okay.
In some special cases, you can reduce to this situation, and then you can rewrite everything in terms of Hilbert space. But in general, you can't. Okay. So like here we have like the new idea for what are our spaces of concern, what are observables. We have some new geometric structures. So basically, it's like kinematic setting. And now the idea is to use those geometric structures on the spaces of quantum states to define dynamics. And using the relative entropy, one can define the generalization of this, what are Luther's rules, and this is exact generalization. And using Hamiltonian flows defined by this Poisson structure, it's not symplectic, but it always allows to define, it's a very nice thing, because it's so-called Banach-Lie Poisson structure. It always allows to have well-defined Hamiltonian flows. So there is also generalization of unitary evolution, but in both mappings are generally nonlinear. So you have like one mapping that generalizes projective measurements, another mapping that generalizes unitary evolution, and so like this, they're joining them together. We have like generalization of like standard.
This Poissonian structure is from the
it's
multiplication in this.
It's a conjoint. Yes, it's like this. What was done by Bona and G.H. Okay, and actually I will tell you right now about this. So this is like just some pure mathematics. Actually I was thinking whether I should show it to you or not. But there is like to be just mathematically strict. I want to mathematically exact. I want to tell about this. So there is basically when one wants to. There is a problem when one wants to generalize symplectic theory to infinite dimensions, and it's pretty hard. And the idea is that maybe one can have something that is not symplectic, but nevertheless one can have well-defined Hamiltonian flows and well-defined structure. And the solution to this problem for quantum states was found by Bona, and later this was like made more abstract by Giebis and Ratio. And as a result, we have a notion right now. We have a notion of Banach-Lie Poisson spaces, which is both Banach space, Banach Poisson manifold, and allows for a very nice relationship between dual of the Banach space and the space of smooth functions. I think I will.
Excuse me, I didn't understand your comment, because in the case of quantum mechanics, there is absolutely no problem with this infinite dimensional symplectic space. Everything goes smoothly. There is a perfect functional analytic framework. Both omega and G are perfectly defined, and everything works perfectly.
When I think of infinite dimensions, I don't mean...
The space is infinite dimensional. It is precisely the same space L2 or L squared, and everything is perfectly...
My comment was on geometric part of it. My comment wasn't on Hilbert spaces. Well, it's natural
No, but neither was mine, because I only claimed that this idea to translate quantum dynamics into a Hamiltonian flow on infinite dimensional symplectic space is perfectly okay. There is absolutely no
I've never,
obstacle.
maybe I'm not updated enough with the knowledge, but I've never read a paper in which would be the claim that this full geometrization that is done in the case of CPN is
trivial.
translated.
It is just trivial. Everything works smoothly. L square is symplectic space where omega is just imaginary part of the scalar product, and everything works.
I'm not sure whether all theorems would pass. I mean,
Yes, I know.
Okay. So thanks for updating. But then, even then, I think that there is my statement could be defended on the level that infinite dimensional Hilbert space is not the same as, I mean, it doesn't solve the problem of unitary and equivalent representations. So, in some sense, it's,
Yeah, this another problem.
yes, I agree. But in the sense that, in this sense, there is still a problem with infinite dimensionality. Yeah, not of the Hilbert space, but of the generality of quantum formulas. But I would be happy to get the reference, because I always was meeting for this setup. I really was always meeting the finite dimensional texts. So I don't know basically the paper where it's done. Okay, so basically there is some nice structure, some nice mathematical structure that allows to deal with well-defined Hamilton equations, and which have unique total maps and unique Hamiltonian flows. And now the thing is that how it works in the quantum case, which is the only one that we really need here. So the starting point is that one can consider all self-adjoint trace class operators. So it's a bit more than just positive part identified with non-normalized quantum states. And one can consider this, one can equip this space with smooth manifold structure, and this modeling manifold is basically the space itself. So one says that
What is it, this SA?
Oh, it's Schatten, it's like first Schatten class, so it's trace class operators.
No, SA.
Self-adjoint.
Oh, sorry. yeah, self-adjoint. Okay, and so basically it amounts to saying that the tangent spaces are isomorphic to the space itself, and then cotangent spaces are defined by duals. And this is like there is a manifold structure. Then those things that are written here, they actually guarantee that we deal with well-defined Banach-Lie Poisson manifold. And then the Poisson structure, which is like the main thing here, is defined this way. So basically we take arbitrary smooth functions on self-adjoint trace class operators, and their derivatives are in the algebra itself, so we can calculate commutator. And this way we define the Poisson bracket between them. This was done for the first time. It was done by Bona, and then Ogiewicz generalized it to all W-star algebras. So if we have a space of quantum states that is well-defined smooth submanifold of the structure, then every smooth function on it defines a Hamiltonian vector field. And now I will recall that general definition was that observables are defined as arbitrary functions. So we have that smooth observables define Hamiltonian vector fields. And in each observable in old sense, like in this quantum mechanical sense, self-adjoint operator, self-adjoint element of the underlying algebra, determines the corresponding observable in the new sense, like basically as an affine function. So having we can take arbitrary smooth function, and the Hamilton equation takes the form so this is nice thing. I'm just one notice. I'm writing everything in terms of density matrices to make it somehow understandable. But this is just working with this type 1 factor case. But all those structures have generalization to all arbitrary W-star algebras. This is the main point of it. And this is like the solutions of it are, it's not a group of unitary operators, it's like a cocycle which has satisfies such condition. However, if we take smooth function that is defined by the old school observable, we precisely recover ordinary unitary evolution. So this is an exact generalization of unitary evolution provided by purely geometrical terms on those spaces of quantum states. Okay, so now the second structure. So quantum distances. I call it distance because it's kind of useful and short. But have in mind that it's not necessarily symmetric at all. Like the starting point right now is just to require one single property, this one, and to prove further properties, one would require sufficient additional conditions for those properties. And okay, so like the standard thing that is known probably by most of you, or if not all of you, is like Omegaki entropy. It was generalized by Araki to arbitrary W-star algebras. And there are like, here are various different relative entropies that are used by people for different purposes of statistical estimation and so on and so on. So this is like what I told you before, that one can choose some quantum model that is relevant for his statistical purposes and propose some specific way of measuring the distance between quantum states. And then start to work with those things and try to see what can be produced. Okay, so now this is like, so here I told you about like second kinematic structure.
Excellent question. So this unitarity in quantum mechanics, maybe there are some different reasons of unitary evolution, but the main is that the probability is constant, or the distance between the states is constant. Okay?
Mm-hmm.
So under your evolution, what is something which will be constant also?
Well, there is a class of relative entropies for which are preserved under unitary operators. Yes.
Under your operators, I mean, under your evolution.
Yes. This is basically like from Pell's monotonicity theorem. There's like full class. Basically, this class of entropies is stable under those conditions. Okay, so now I want to construct another form of quantum dynamics using this second geometric structure provided by relative entropy. Okay, so like consider some space of quantum states that you are interested in, and some state inside, and consider some. It might be subset, but actually it might be somewhere else. This picture might be a bit misleading. Just some set of states that is determined by some constraints. Okay, and now let's consider such problem. We want to find a point in this space. We want to find a point that satisfies those constraints, so it's inside the space, but which is as close to this state as possible when the notion of being close is defined by this relative entropy that we have. So we put this original state in one slot. We put this state that we search for in the another slot. We are trying to find infimum of this functional within the space given by these constraints. And then, if we find it, if it's unique, if it exists and is unique, then we take it argument. I mean, we take this point which solves this problem, and we call it entropy projection of this original guy. Naturally, there is no guarantee that for arbitrary choice of D and Q, this problem is well posed. However, you can consider that if you have given some specific entropy, then you can investigate what type of for what type of constraint sets you will get unique and well, you will get a result that exists and is unique. And basically, actually I can immediately give both examples. You might think of it as follows. If relative entropy is understood as a method of inference, then there is only specific method of inference gives you well-defined results only with respect to specific data types. You can think of those forms of constraints as specific data type. And it's like, it's data type sensitive. So, for example, if you will use this, this relative entropy that is defined by square of Hilbert-Schmidt norm distance, then specific, then the good data type are embeddings of linear subspaces of Hilbert-Schmidt space. And on the other hand, for this ordinary relative entropy, this would be like affine sets that are defined by constant expectation value. So it's the case by case what are the good Qs that solve this problem, but it's like the notion that might be found useful. And now I will try really to pass to the good application of it. So here are once again Wither's rules, like the standard prescriptions for quantum mechanics, for non-sophisticated quantum mechanics at least, without TP-CP maps. And there are like few different proposals that one should, or it would be very reasonable or seductive, if you prefer postmodern phraseology, to consider those rules, or at least this one, as an analog of the Bayes rule for probability theory. And there are some arguments given why it's plausible consideration. However, there was really never something like some sort of really mathematically compelling reason for this given. In the meantime, there was obtained a series of results showing that Bayes' rule can be, well, is a special case of entropic projection, which is very nice because it means that something that is considered as a very, very fundamental and standard principle for change of information state, at least in the Bayesian approach to probability, actually is just a special case of a broader framework, which is very information theoretic-ish. Well, so this is the question whether maybe those rules can be derived also from constraint maximization of relative entropy, and the result is so. And this is pretty nice, I think. Which means that both those prescriptions for quantum measurement, I don't like this phraseology, but well, nevertheless, like orthodox updating rules for naive quantum mechanics they are like they are indeed very similar to Bayes' rule. They come from the same principle of you might say information dynamics, or you might say statistical inference.
You have 5 minutes and you have still 8 transparencies, so could you somehow shorten?
But we are almost at the end. I have, yeah, because I have like few things that I may skip. I prepared for myself for this. This is okay. So for example, this is one thing that I will skip in 10 seconds, telling you that also more general forms of Bayesian updating rules that are considered in advanced Bayesian literature were derived by some people from constraint relative entropy maximization, and one can propose exact quantum analogs and also derive it from entropic projections. One can also go further with this idea of entropic projections and consider quantum entropic instruments and effects, which I will not tell you about because it's not enough time. And to summarize, like using two geometric structures, so choice of specific relative entropy and a choice of specific Hamiltonian smooth function which defines Hamiltonian vector field by means of uniquely given quantum structure. One can consider two forms of dynamics on spaces of quantum states. And those can be, from the perspective of someone who is into Bayesian reasoning and statistics more than into analyzing the spectra of atoms, those two structures can be understood as respectively like a specific convention of causality and non-causal inference. And when one joins those two maps together, they strictly generalize unitary evolution followed by projective measurement. And right now, I'm together with one student and also a friend of mine. We are working on proving that actually
What is CPTP?
completely preserving, completely positive trace preserving. That all maps can be constructed like this. If yes, then one can say that this is not only the alternative for naive quantum mechanics, but also the alternative for more advanced quantum mechanics. And now I will tell you, I'm actually thinking whether I will tell you more about semantics. Well, yes. How much time do I have?
2 minutes.
Great, fantastic. So now you can ask me, okay, so what's about all the story? Like, so far there was kinematics and dynamics. There is still nothing told how to construct those things. And this was like one of the main problems of, I would say, algebraic approach, that it's nice to assume that we have this algebra, but actually the question is how to construct it given a specific experimental situation. And I don't have good answers for it. However, there is nice and I think suggestive insight that I want to leave you with. So the thing is that like many W-star algebras, maybe all relevant W-star algebras, can be constructed from measurable groupoids. And you might think of measurable groupoids as a generalization of measurable set. So basically, when you have like measure theory, you consider, okay, you have the sigma algebra of subsets of a given set, and set consists of points. In case of measurable groupoids, you have also, you don't have just sigma algebra that is just subsets. There are also morphisms between those subsets and specific relationship between measures on it. So it's like more advanced. You might think of it as more advanced subject of statistical inference. So basically, like while W-star algebras are very non-descript for the statistician and like for the statistical thinking, and for physicists probably too, it can be produced from something that is more interesting, and actually maybe one may think of it more direct terms. Basically, instead of just considering elementary events, one can consider in subsets of those. One can consider that the structures about which we do inference, they have internal possible morphisms, and we start already from the just more interesting situation that we discussed. Okay, construction of quantum models. This problem is precisely like construction of probabilistic model. There is no change here. So if you don't know how to construct your probability model in statistics when you analyze some situation, it's the same with quantum case. Nothing changes. It's just it's like integration over some space. That's all. And regarding nonlinear observables, one may think that in general, like at least in finite dimensional situations, here we have some quantum model, like these are like quantum states here, whatever, and I use such thing, and here is like some space of parameters that we consider as the parameters in which we do the experiment. So models should be parameterized by those parameters if we think that this model can be if this data is sufficient to analyze this model, then this model should be covered by those parameters. Okay, so here is some experimental function of those of the space, and here is some nonlinear observable. I don't know whether I'm actually in agreement with this notation. Probably it's like here, and now it should be. So basically, this is times rho of theta, and here we have like rho of theta. Yeah. So the idea is basically that nonlinear observables, if you have a parameterization by some parameters of the model, then nonlinear observables can be translated to just arbitrary nonlinear functions of experimental parameters. Okay, and this is something what I already told you, and here's the proof that whether I'm wrong or right or whatsoever, at least I was thinking a lot about this. Thank you.
Well, if you apply this philosophy that there is a more general framework, just to something which is relevant, like even free electromagnetic field, what would be the extension of the standard theory that is allowed by this model, and how can you test it?
So this is an issue of model construction in this framework, and there are like model construction requires to provide specific choice of this space of quantum space.
I'll give you a specific case: electromagnetic field, free electromagnetic field. The question is, what new comes out of this study as far as this physical object, very important physical object, is concerned?
This would require to provide specific description of a specific experimental situation that is under
Of
construction.
course, there are many experimental situations. Has there been an effort to connect this with something relevant?
This is a good dialectic in the sentence, so I cannot answer you neither no nor yes, because because I consider this what I've done as relevant. So I can tell you that I have not been analyzing
I mean that
specific.
can be falsified by experiment.
Framework for model construction in principle cannot be falsified or verified. It might be considered as a useful tool for people who are constructing models.
But we have a model. This model is called electromagnetic field.
Yeah, but this is ontic perspective. So there is the ontic perspective is that there is an electromagnetic field out there. The epistemic perspective would be, okay, we do some specific type of experiment. Like we have some specific type of experimental situation. Then we have some specific control parameters in this experimental situation. Then we used to do such and such statistical inference on those parameters, estimate some quantum states based on those parameters, estimate some specific observables that are optimal with respect to this, what we think the situation is. Usually one does both. I mean, in modern quantum measurement theory, people estimate both observables and states, and which actually shows that they don't believe in eigenvalues anymore. But at the end, one has specific quantum statistical model for the situation, and then which has implicit assumptions about what is the criteria for best estimation, and specific assumptions for internal dynamics, so for the form of causality, and explicit assumption about what are the relevant observables. So if you take such situation and you specify those data, you might ask other additional parameters that cannot be achieved while keeping to eigenvalue dogma, or whether no. Then you take the situation, you take your knowledge and insightfulness about based on your experience with constructing this specific sort of models, and you propose something else. I'm to my I don't know whether satisfaction or dissatisfaction. I think to my reality, I'm more accustomed to functional analysis than with doing experiments. So I cannot answer you to this question, but I can give you also an example when such things work. So when you do maximum entropy approach to thermodynamics or statistical mechanics, the ideology is very, very close. So you provide your set of relevant observational epistemic parameters, like you can say temperature, volume, something else. You specify what you have measured as averages. You said that averages are assumed to be equal to expectation values. Then you maximize entropy subjected to this constraint, and you produce a specific model. If the predictions of this model they don't fit completely what you measure further, then you say, oh, maybe I have assumed that incorrect dynamics, or maybe there are additional control parameters that I have not taken under consideration when producing my model. So, but this is something that you can do only when you have a specific experimental situation under consent. So, I'm not an expert in experimental situations.
Okay, so I understand that in the community that you're part of, there's no interest in experiments.
Oh, I don't know. I think that I belong mostly to community of my own research. So, and the answer, if we accept this assumption, then the answer is no. I'm very interested, but the problem is that the day of work has well, at least not. Well, by definition, it has 8 hours. Yeah. So.
But you never had a temptation to make contact with the other.
The answer is no. Actually, I talked with people, but I never had enough time and for moving from trying to fix details of mathematics into, well, if we will be talking like 5 years from now, if someone would be happy to still fund my research, then I would be happy to answer yes. I was analyzing specific experimental situations, but I think that this within the specific context that I presented, this sort of point is relevant, but using this point as a criticism is not yet relevant.
May I ask a question? Do I understand correctly that with all these generalizations, you are still distinguishing one very important parameter, namely time? Is that right?
Yes and no. So, yes, because I did it here. No, because I did it, not because I needed to do this, but because I'm mostly interested in backwards compatibility, because I want to, at the end of the day, I would like to see those differences in predictions. So, coming back to the issue, just the central point, which is here, here. So, well, I just use the fact that I have naturally induced Poisson structure, use this to define Hamiltonian vector field, and then this is additional assumption that I want to model whatever I call causality within the system by those Hamiltonian vector fields. It's not necessary by any means. I can model the intrinsic causality of quantum systems by whatever. I would have whatever automorphism or even endomorphism of quantum model, or just mapping of quantum models. I could actually use also entropic updatings also as a model of causality. The point is that if I would go with such generality, what I would lose and what I would gain. Yeah, right now at this stage of development of the project, I would not gain much. I would just gain, generality is not a value for itself. Yeah. And like I'm keeping to backwards compatibility with this time, because this is the way physicists are trained to construct their models, and most of the models that we have right now in physics, that they have causality, time parameterized causality, not a more general abstract causality that is used in statistics. So it's not necessary. I do it to keep with physics as known.